Right now, as you listen to this, an invisible impact is happening on the far side of our own star. An object from another sun, older than our entire solar system, is moving through a storm we cannot see. A wave of superheated plasma is slamming into it, carrying the energy of millions of nuclear explosions. The object itself has slipped behind the sun, hidden from every telescope on Earth. We can only model the collision on computers and wait. NASA has quietly flipped its planetary defense switch for something that cannot even hit us. An ancient visitor is being stress tested by our star, and we do not know what will come out the other side. Stay with me, hit like, and subscribe, because this may be the strangest experiment nature has ever run for us. To understand how we got here, we have to start with a flare no one on Earth could see. On an October day in 2025, a team of solar astronomers in Russia were looking at the half of the sun that always faces away from us. They were using spacecraft and radio techniques that can sense eruptions even when they happen over the horizon. What they found was not a routine burp of activity. It was one of the strongest solar explosions of the entire cycle. A monster eruption that hurled billions of tons of plasma into space at astonishing speed. Normally, when you hear about a huge solar storm, the next question is simple. Is it coming toward Earth? This time, the answer was no, which is why you did not see emergency headlines or power grid warnings. The cloud was not pointed at our planet at all. When the Russian team traced its path through space, it seemed to be aimed at nothing in particular, just empty, dark. Then they overlaid the projected position of a new object that had recently been added to the tracking charts. That object was 3I Atlas, the third confirmed interstellar visitor ever seen passing through our solar system. Its path carried it right into the predicted corridor of the plasma cloud. Not near it, not vaguely in the neighborhood. The model said the cloud and the object would occupy the same region of space at nearly the same time. For at least a day and a half, maybe longer, this ancient body would be immersed in a storm of charged particles racing outward from the Sunday. You can imagine the mood in that observatory when the numbers converged. They had just watched our star launch a natural particle cannon at something that did not come from here. In their internal write-ups, they joked darkly about giving any hypothetical aliens a taste of solar weather. But beneath the humor was a serious unease. This object is a scientific treasure. Losing it to a violent outburst would be a tragedy. Watching it react in real time could be priceless. The basic physics is simple and brutal. A cloud of plasma is not a soft mist. It is a torrent of ionized gas, shot through with magnetic fields, moving at hundreds of thousands of kilometers per hour. When it slams into a solid body, it can strip material off the surface, rearrange electric charges, and dump huge amounts of energy into whatever it hits. For a fragile comet, that might mean dramatic brightening, violent jets, even complete breakup. For something more solid, the effects are harder to predict. Heating, cracking, electrical discharges flickering across the surface. Now, put that in context. 3I Atlas is not just any comet. It does not belong to the sun the way our local comets do. Its orbit is hyperbolic. That means once it leaves, it will never come back. We get one pass, one chance to watch it, measure it, and squeeze as much information as we can out of this visitor from a star system we will never see. A natural solar experiment is about to alter that one chance in ways no one can fully model. This is the moment when the story shifts from pure astronomy to something more like strategy. On that same October day, as the solar flare details were still being refined, NASA, the National Aeronautics, and Space Administration issued a carefully worded notice through the International Asteroid Warning Network. It announced a formal planetary defense observation campaign for 3I Atlas. Not for an asteroid on a collision course with Earth, not for a known impact threat, for an interstellar object that poses no direct danger at all. Publicly, the notice talked about an opportunity to test global coordination. It mentioned the unusual trajectory of the object and the chance to rehearse tracking a fast-moving target with uncertain forces acting on it. Read that casually, and it sounds like a drill that just happens to use an exotic comet as a convenient prop. But buried in the language was a phrase that rang alarm bells for people who follow these documents. The object creates unique problems for prediction and tracking. Not unique opportunities, unique problems. What kind of problems? In principle, every chunk of rock or ice in space should follow paths we can predict from gravity and the known push of sunlight and gas jets. Planetary defense is built on that assumption. You see something, you measure it, you compute its future positions years into the future. For 3I Atlas, those predictions keep needing small but persistent corrections. The deviations are not huge, yet they refuse to line up neatly with the usual explanation, which is chaotic outgassing from sun-warmed ice. If you are responsible for guarding a planet, an object that does not quite behave according to the rulebook gets your attention. Even if it is not heading toward Earth, it is a perfect stress test for your warning systems. How well can you model something that refuses to be boring? How quickly can you mobilize telescopes across continents when a target ducks behind the sun and then reappears? Could you do the same if the next object did point toward us? These are the questions hiding behind the polite language of an international exercise. So, here we are. An ancient body from another sun is being raked by a solar storm on the far side of our star. Our instruments cannot see it. Our models can only guess how it responds. And our planetary defense infrastructure, built to watch for rocks that might one day strike Earth, has been pointed instead at a single strange comet that comes from the deep between stars. In the next parts, we will peel back why this particular visitor earned that level of concern. To see why scientists are so fixated on this one object, we have to rewind to when it first appeared on our screens. On the 1st of July, in 2025, the Atlas survey system in Chile picked up a faint moving point among thousands of stars. It was exactly the kind of discovery the system was built for. Another routine dot that might turn out to be a harmless asteroid or a distant comet. At first, no one watching that data feed had any reason to think history had just changed. The routine step after any new detection is orbit calculation. You measure the position over a few hours, plug it into the equations, and watch the computer spit out a path. That path tells you if the object loops around the sun with a nice closed curve or swings in on a one-way track. When astronomers ran the numbers for this newcomer, the result was a little slap in the face. The curve did not close. The orbit was hyperbolic, meaning the object was not bound to the sun at all. It was diving in from interstellar space, and once it left, it would never return. That instantly placed it in one of the rarest clubs in astronomy. Before 3I Atlas, we had confirmed only 2 interstellar visitors. The first, discovered in 2017, was Oumuamua, a bizarre, elongated object that tumbled through the inner solar system like a shard of something broken. The second, in 2019, was Borisov, which at last looked like what people imagine when they hear the word comet, a bright head and a graceful tail, behaving mostly by the book. 2 visitors, 2 very different personalities, and now a third had arrived to complicate the story. Oumuamua shocked the community because it did not act like a normal comet at all. It showed no clear coma of gas, no obvious tail, yet as it receded from the sun, it gained a tiny extra push that could not be explained by gravity alone. That non-gravitational acceleration lit up debates about exotic explanations, from unusual outgassing to radiation pressure to far stranger ideas. Borisov, on the other hand, felt almost comforting. It shed gas and dust in familiar ways. Its composition was different from local comets, rich in carbon monoxide, but it fit into known physics without too much stretching. So when astronomers realized they had a third interstellar object on their hands, the big question was simple. Would 3I Atlas behave like Oumuamua, like Borisov, or like something else entirely? The early measurements suggested something new again. First, there was the size. Based on its brightness and how its light changed as it rotated, the team estimated a solid core between 2 and 6 kilometers across. That is a chunk of material roughly as tall as a major mountain, compressed into an almost spherical body of ice, rock, and frozen gases. From that size and how it reflected sunlight, scientists estimated a mass on the order of tens of billions of tons. Picture an object with 30 billion tons of inertia barreling through our system at more than 200,000 kilometers per hour relative to the Sunday. It is not a pebble. It is a deep time boulder, carrying momentum built up over billions of years of wandering through the galaxy. You start to understand why everyone suddenly cared where exactly it was going and what forces were acting on it. The trajectory itself added another layer of intrigue. A hyperbolic path says this thing is not a member of the Sun's long-term family. It is a tourist passing through once, then vanishing into the dark again. That alone makes it precious. But as more observations came in, the details of that path began to look oddly convenient. The orbit would carry it close to Mars in early October, then past Venus, then near Jupiter. 3 world flybys on a single pass, each close enough for serious observation from spacecraft and ground-based telescopes. If you are generous to randomness, you can say the solar system is a busy place. Any object threading its way through will have some chance encounters. Still, the specific sequence of close approaches raised eyebrows. Mars first, right as its orbit and the comets line up for optimal geometry. Venus next, a bright inner world, then the gas giant that dominates the outer system. You could not design a much better survey route if you were deliberately trying to inspect the major planets in one run. For most scientists, this is still a striking coincidence rather than a plot, but it is the kind of coincidence that sticks in the back of your mind. Even before it came within range of those planets, 3I Atlas started to misbehave in a more physical way. At a distance from the Sun, where most comets are still deep frozen and quiet, this object began to show signs of activity. Telescopes detected water leaving the surface at a rate that should simply not happen so far out, where sunlight is weak and temperatures are brutally low. Comets usually wake up closer in, when solar heat has a real chance to melt surface ice and turn it into gas. This one seemed eager, almost impatient. That was the first hint that there might be more going on inside than a passive lump of ice. Some researchers suggested that perhaps 3I Atlas is rich in very volatile compounds that can evaporate even in weak light. Others pointed to structural cracks that might expose fresh material to space earlier than usual. Those are sensible natural ideas, and they may all be part of the answer. Yet as the observations continued, another pattern emerged. The small extra pushes in its motion, the non-gravitational accelerations, looked smoother and more consistent than the chaotic sputter you expect from random jets of gas. In principle, nothing in this story demands an artificial explanation. Nature is very good at surprising us. Still, if you step back and list the early facts, they make a strange little chain. The third ever confirmed interstellar object, bigger and heavier than the others, wakes up too early. Its path just happens to skim past 3 major planets in sequence. Its subtle course changes do not quite match the messy behavior of regular comets. Scientists did not call it a probe, they called it a puzzle, and as more data poured in, the puzzle only deepened. 3I Atlas was supposed to be a quiet rock at first. At 3 astronomical units from the Sun, roughly the distance of the asteroid belt, comets usually sit in deep freeze. The sunlight is weak. The surface temperature is far below the point where water ice should turn to gas. In the standard playbook, this is the sleepy outer act of a comet story. Nothing much happens until it moves closer in. Except this time, the script went sideways. When NASA pointed the Swift Space Telescope toward the new interstellar visitor in October, they expected a faint object with little or no activity. Instead, the data showed water pouring off the surface. Roughly 40 kilograms every second, enough to fill a large bathtub in the time it takes you to blink. For a comet that far from the Sun, this level of water production should be close to impossible. According to the models, there is simply not enough heat to drive that much ice straight into vapor. This is the first big behavioral red flag. Comets are supposed to be simple. The sun shines, the surface warms, volatile ices sublimate, gas escapes. That escaping gas carries dust, creates a coma and a tail, and gives the nucleus little kicks that alter its path. All of this usually happens closer in, so if 3I Atlas is boiling water early, then something else must be adding energy. Either the ice is made of unusually volatile mixtures that react to very weak sunlight, or the interior is not the inert freezer we assumed. Several natural explanations are on the table. One idea is that the comet is loaded with ices like carbon monoxide that can evaporate at very low temperatures and drag water out with them. Another is that its surface is riddled with fractures, so even tiny thermal changes can trigger large jets from freshly exposed layers. Some researchers suggest there could be slow chemical reactions happening inside, releasing heat bit by bit. There is even the possibility that long ago, in some other star system, the object passed very close to a star and stored heat that is now leaking out again. None of these require anything artificial. Nature can be messy and generous. Yet as teams continued to track the motion of 3I Atlas, the pattern of its little course changes started to look odd. Every active comet experiences non-gravitational acceleration, tiny pushes from jets of gas that act like random thrusters. For most comets, those pushes are jittery. They change as sunlight angle changes, as vents open and close, as the nucleus tumbles. When you plot their motion, you see a kind of noisy wiggle imposed on the clean gravitational path. With 3I Atlas, the wiggle looks too tidy. The extra acceleration seems smooth and consistent, more like a gentle, continuous push than a chaotic sputter. This is still a subtle effect, measured in fractions of a millimeter per second in its speed, yet comet specialists notice when the math feels wrong. The official Planetary Defense Notice phrases it politely as anomalous behavior that complicates trajectory calculations. Off the record, some astronomers describe it more bluntly: this thing flies like a mission. That phrase caught the attention of Avi Loeb, the Harvard astrophysicist who has already made waves arguing that Oumuamua might have been artificial. He is used to controversy, and he knows that most of his colleagues disagree. Still, he points to several features of 3I Atlas that match how a smart spacecraft would use a star. The smooth extra acceleration looks like ongoing control rather than random venting. The timing of its closest approach to the Sun lines up with a classic trick of orbital mechanics called an Oberth maneuver. The Oberth maneuver sounds like science fiction, but every interplanetary mission uses some version of it. The idea is simple once you see it. When a spacecraft falls deeper into a gravity well, its speed increases. Near the closest point to the planet or star, it is moving fastest. If you fire engines at that moment, you get more change in total energy than if you used the same fuel elsewhere in the orbit. In other words, you get extra bang for your propellant by burning when you are already moving fast. It is like kicking a swing at the exact right moment to send it higher. Loeb suggests that 3I Atlas may be doing something similar. Its perihelion, the point of closest approach to the Sun, happens during what solar physicists call perihelion season, a period when our star is especially active. The object swoops in, experiences maximum gravity and maximum possible heating, and then emerges on a path that appears slightly adjusted compared to what pure gravity and random outgassing would predict. If there were any kind of active system on board, even a very weak one, perihelion would be the perfect time to use it. Again, this is speculation. The mainstream view remains that 3I Atlas is a natural comet whose quirks expose holes in our models. Yet the coincidence stack is uncomfortable, an object that wakes up too early, water production where there should be none, a thrust pattern that looks more like deliberate course correction than chaos, a trajectory that threads past Mars, then Venus, then Jupiter, as if it were drawing a survey line through the solar system. For planetary defense planners, the important point is not that this proves anything about alien technology. The important point is that here is a body which refuses to play by rules that work very well for thousands of other objects. If you want to understand what your warning systems can really handle, you test them on the weirdest target available. 3I Atlas has become that target. It is a comet that behaves like a mission, and that makes it both fascinating and slightly unsettling. So far, we have watched 3I Atlas act strangely. It wakes up too early, vents water where it should be frozen, and flies its path with the calm of a planned mission. Behavior alone would make it interesting. Then the chemistry arrived, and the story jumped from weird to genuinely alien. When the James Webb Space Telescope finally turned its infrared eyes toward the object, scientists expected a familiar recipe, the sort of chemical soup we see in comets born around our own Sunday. What they found instead was a comet that seems to have been cooked in a completely different kitchen. Typical comets from the solar system are water creatures. Their ices are dominated by frozen H2O, with smaller amounts of carbon dioxide carbon monoxide, methane, and ammonia mixed in. The exact ratios vary from one comet to another, but water almost always wins. Even the oddballs tend to stay within a certain range. A comet that is rich in carbon dioxide might have close to equal parts water and CO2. Some push that balance a little further, but water still leads the chorus. 3. Atlas ignored that rule. The spectra from James Webb showed carbon dioxide pouring off the object at roughly 8 times the rate of water. 8-to-1 CO 2 over H2O. That is not a small tweak. That is an inversion. It is as if someone flipped the volume knobs on the comet chemistry panel so that the background gas became the main act and the usual star was turned way down. In our catalogue of comets, we do not have anything quite like this. Those gas ratios are not random trivia. They are clues to where and how a comet formed. Think of a young star system as a vast rotating disk of gas and dust with a temperature gradient. Close to the star, everything is hot. Further out, it cools. Different molecules condense into ice at different distances. Water needs it relatively chilly to freeze. Carbon dioxide can freeze at higher temperatures. Where an object forms in that disk determines which ices it picks up and how much of each. In our own system, that pattern created familiar zones. Near the young sun, it was too hot for water ice to survive, so rocky planets formed dry and later acquired volatiles. Further out, beyond what scientists call the snow line, water condensed in huge quantities, loading comets and icy moons with frozen H2O. Carbon dioxide is present too, but usually as a minor partner. The chemistry of our comets reflects that history. They are children of a disk where water had plenty of room to lock in. A comet with 8 times more CO2 than water tells a very different story. To get that balance, it must have formed in a region of its original disk that was hot enough that water could not easily condense, yet still cool enough that carbon dioxide could. That is a narrow window in temperature space. Too hot, and even CO2 stays gas. Too cold, and water would dominate again. This is why some scientists describe 3I Atlas as baked and boiled. Baked, because it lived in a hotter zone than our icy bodies. Boiled, because water seems to have been driven off or prevented from ever freezing in large amounts. What kind of star creates a disk like that? One possibility is a star more massive and hotter than the Sunday. Such a star would push the regions where water can freeze further out, leaving intermediate zones where carbon dioxide can still condense while water stays vapor. Another is a disk with an unusual chemical makeup, richer in carbon-bearing compounds from the start. In that case, even if water did freeze in some places, carbon dioxide could overwhelm it in others, creating pockets where CO2 heavy bodies formed. We may never reconstruct the exact nursery of this comet, but the important point is that its chemistry does not fit the formation zones we know well. It is not just a solar system comet with slightly tweaked ingredients. It is the product of a protoplanetary disk that obeyed a different balance of heat and chemistry. In that sense, 3I Atlas carries a chemical fingerprint of a star system that no longer exists in any simple way we can see. Every time the sun heats its surface and drives off gas, that fingerprint becomes readable. The glowing coma around the object is not just a pretty haze. It is a thin, temporary atmosphere whose spectrum encodes the conditions of a long-vanished place and time. Instruments like James Webb spread that light into a rainbow and pick out the telltale lines of different molecules. Each line is like a bar of a tune from another world. In this case, the melody is dominated by carbon dioxide in a way that almost shouts, "This is not from around here." There is something quietly mind-bending about that. We are not just looking at a visitor from another star. We are sniffing the air of a planetary nursery that may have been active before our sun had even formed. The ratios of gases tell us about its temperatures, its pressures, its chemical richness. Combined with dynamical models and age estimates, they suggest that 3I Atlas was born in a stellar neighborhood with different rules, perhaps in a busier, more violent era of the galaxy, when massive stars were common and disks boiled off water with ruthless efficiency. All of that is encoded in a faint fuzzy patch of light near a distant planet, read by mirrors and detectors, and then turned into numbers on a screen. No alien plaque, no engraved message, just chemistry. Yet that chemistry already tells us that the galaxy is more diverse than our one example of a solar system might suggest. And in the case of 3I Atlas, it sets the stage for the next twist. Because if this object really did form in such a harsh environment billions of years ago, another question comes crashing in behind it. How can something this old, from such a baked and boiled birthplace, still be so alive today? When you first hear the age estimate for 3I Atlas, it sounds like a mistake. 7 to 10 billion years, older than the Sunday, older than the Earth, older than any rock that still exists on our planet. We are used to thinking of comets as ancient, but ancient within the story of our own system, 4.5 billion years or so. This thing predates the entire stage on which our story takes place. It is like finding a fossil that was already old before the planet that discovered it even existed. Astronomers did not pull that number out of nowhere. They worked backward from the path. Once you know an object is not bound to the sun, you can track its incoming direction through space with great precision. Then you embed that direction in models of the Milky Way, which include how stars orbit the galactic center over billions of years. By rewinding those orbits, you can ask a simple question: how long has this object been wandering freely instead of being tied to a single star? The answer, within the limits of the models, is staggering. 3I Atlas seems to have been cruising through interstellar space for longer than our solar system has been around. It is not a recent exile from a neighbor star that just happened to pass by. It is a relic from a time when the galaxy itself looked very different. 10 billion years ago, the universe was young, roughly a third of its current age. The Milky Way was still assembling. Star formation was faster, explosions were more common, heavy elements were rare. Somewhere in that rough early epoch, a star formed with its own swirling disk of gas and dust. In that disk, icy bodies condensed. One of them, in a region hot enough to bake away most of its water, but cool enough to trap carbon dioxide, became what we now call 3I Atlas. It orbited its parent star for a while. Then something dramatic happened. Maybe a close encounter with a giant planet, maybe the slow tug of gravitational resonances, maybe a near miss with another star that passed too close. Whatever the trigger, the result was ejection. The comet gained just enough speed in just the right direction to escape its home system and fall into the wide ocean between stars. From that point on, its journey stopped being a neat orbit and became a vast, looping track around the galaxy itself. It circled the center of the Milky Way again and again, passing through spiral arms, drifting above and below the galactic plane, weaving through the changing gravity fields of billions of stars. Out there, far from any steady source of heat, space is unimaginably cold. Temperatures hover only a few degrees above absolute zero. Chemical reactions grind to a near halt. Ice does not sublimate into gas because the surrounding vacuum is already empty and frigid. Time stretches. Millions of years begin to look like short chapters. For most of its existence, 3I Atlas was in a kind of cosmic cryogenic storage, its interior frozen in the state it had when it left its home star. You might think that such deep freeze would preserve it perfectly, yet there is a catch. Interstellar space is not completely gentle. Cosmic rays, high-energy particles from distant supernovae and other violent events constantly batter anything that drifts between stars. Over billions of years, that radiation can break chemical bonds, drive off the most delicate compounds, and slowly harden exposed surfaces. If you left a block of ice outside for ages while tiny bullets of energy hit it, you would expect the outer layers to become crusty and depleted. This is where the paradox appears. An object that old, weathered by cosmic rays for billions of years, should to be tired. Its surface volatiles should be mostly gone. Its remaining ices should be harder to evaporate. When it finally enters a new star system, we would expect only a modest response. Maybe a faint coma. Maybe short-lived jets from sheltered pockets. 3I Atlas does not match that picture. At 3 astronomical units, it was already gushing water at a rate that rivals fresh local comets. How can a body that has been drifting through deep time still behave like a young, lively comet? One possible answer is that we are not seeing the original surface at all. Instead, we may be looking at the freshly exposed interior of something that was once larger. Imagine that for most of its long journey, 3I Atlas was part of a much bigger world. Perhaps a dwarf planet the size of Pluto. Perhaps an icy mantle wrapped around a rocky core. Over time, some catastrophic event fractured that larger body and sent fragments spinning off into space. If our visitor is one of those fragments, then its materials can be both ancient and young at the same time. The atoms and molecules were forged and frozen billions of years ago in that alien disk. Yet the surfaces we now see were only recently open to space, when the parent body broke apart. Recently, in cosmic language, might still mean millions of years. That is long enough to cross the distance between stars, but short enough that the newly exposed ice has not been completely processed by radiation. This idea, sometimes described as recently liberated material, neatly solves part of the paradox. The comet can carry the chemical fingerprint of a very old environment while still having plenty of active ices ready to roar to life under new sunlight. Fresh fractures provide channels for gas to escape efficiently. Crystalline structures that never had to endure eons of direct bombardment can sublimate energetically when warmed, driving that surprising water production far from the sunday. There is another twist. If 3I Atlas is a shard of a larger world, then its history may include not just simple freezing, but geological processes on its parent. Long-lived internal heat from radioactive elements, tidal flexing by a massive nearby body, or repeated surface impacts could all have cooked its interior in complex ways before it ever broke free. The activity we see today might be the final act of processes that played out inside a lost dwarf planet around a long-vanished star. However you slice it, the age estimate forces us to widen our view. This is not just a stray snowball passing through. It is a time capsule from when the Milky Way was noisy and young, carrying the chemistry of a different era and possibly the structural scars of worlds we will never map. The fact that it is still active, still venting, still responding dramatically to our sun after such an unimaginable span means that the galaxy can preserve its stories for far longer than we once dared to hope. And that, in turn, raises the stakes of the current experiment. When a solar storm hits a typical comet, we learn a little more about how sunlight shapes local ice. When it slams into a 7 to 10 billion-year-old interstellar relic that is somehow still alive, we are prodding a fossil that moves. Every puff of gas, every shift in brightness, every tiny alteration in its path is data about both its ancient birth and its long, cold journey. We are not just watching a rock burn. We are watching deep time react. By now we know that 3I Atlas is chemically strange and impossibly old, yet somehow still active. That alone would make it a prize. Then another layer of meaning appears when you ask a deceptively simple question. What exactly is it carrying? Not in the sense of secret machinery or alien hardware, but in the basic sense of ingredients. Because when astronomers broke down the light from its coma, they found something both familiar and unsettling. The stuff around this alien comet looks a lot like the raw material that helped build us. Spectroscopic studies show that 3I Atlas contains water, carbon-bearing molecules, and likely a zoo of organic compounds. Organic in this context does not mean living. It means chains of carbon and hydrogen and other elements that are the backbone of biology. Think of simple alcohols, aldehydes, maybe amino acid precursors. Chemically rich, but not yet anything you would mistake for a cell. It is a pantry, not a person. Still, the overlap with the recipes of life is hard to ignore. We already suspect that comets in our own solar system helped load the early Earth with some of these materials. In the first few 100 million years of our planet, impacts were common. Icy bodies slammed into the surface, vaporized, and delivered both water and complex chemistry to a world that started out hot and dry. There is still a lively debate about exactly how much of Earth's water came from comets versus asteroids versus material locked in from the beginning. Yet almost no one doubts that comets contributed something. They were cosmic delivery trucks for wetness and carbon. Now take that picture and expand it to the galaxy. If our local comets can carry water and organics, and this interstellar comet from a completely different star system carries water and organics, then the implication is powerful. The chemistry needed for life is not a rare local accident. It is a shared language that matter speaks in many places. The building blocks of biology form easily in cold clouds between stars, in protoplanetary disks, on icy surfaces baked by ultraviolet light. 3. I-Atlas is proof that such chemistry can be packaged into a solid body, survive ejection from its home, and travel for billions of years. This connects to an old and controversial idea called panspermia. At its softest, it suggests that the ingredients for life move between worlds on rocks and ice. At its most ambitious, it imagines actual microbes hitchhiking between star systems. The harsh radiation of interstellar space makes the strong version unlikely. Over millions of years, high-energy particles would shred delicate biological structures. Even tough spores would struggle to remain viable over the distances and times involved. But you do not need intact organisms for the idea to matter. The weaker form of panspermia is about chemistry, not passengers. A comet that strikes a young planet can deliver water and organic molecules ready to react. On a warm, wet surface, bathed in sunlight or near hydrothermal vents, those molecules can link up into longer chains. They can form membranes, self-replicating structures, primitive metabolic loops. Whether you believe life is almost inevitable given the right conditions, or an improbable accident, you have to start with raw material. Comets are one way to get that starter kit. 3I-Atlas shows that this process is not confined to one star system. Imagine its long journey. For billions of years it has been orbiting the Milky Way, sometimes passing relatively near young stars with forming planets. Most of those flybys would be distant, but space is big and time is generous. Eventually, one of those passes might bring it close enough that gravity nudges it inward. It could skim through the outer reaches of a new planetary system. It could leave a dust trail that falls onto cold moons, or onto a world where liquid water is just beginning to collect in basins. Picture a planet that formed around some other star 8 billion years ago. It cools, oceans condense, lightning flashes over warm seas. Then, at some point, a fragment of this interstellar comet rains down, scattering its mix of water and organics into the local brew. Does that impact guarantee life? No, but it tilts the odds. It hands that planet a pre-mixed set of ingredients that have already endured harsh radiation, cosmic ray processing, and the strange baking and boiling of an alien protoplanetary disk. In a sense, 3I-Atlas could have been a seed courier long before our world existed. Now flip the direction. If alien comets can reach us, our debris can reach them. Impacts in the early Earth era and later could have ejected fragments of crust and ice into space. Some of those fragments might have left the solar system entirely. Over immense timescales, they too could cross interstellar distances. By the time they arrive anywhere, any original biology is almost certainly gone. But the elements and some of the molecular patterns remain. The galaxy becomes a slow, stately exchange network, with comets and rocks trading chemistry between systems like messages written in a language of carbon and oxygen. In that picture, 3I-Atlas is more than an isolated curiosity. It is a messenger from a traffic pattern that has been running quietly in the background for most of cosmic history. It tells us that the same kinds of molecules we rely on here can form and survive in very different stellar environments. It hints that the question of life in the universe may not be about whether the ingredients exist. They clearly do. The question is how often those ingredients land in the right environment and have enough time to climb the ladder from simple chemistry to complexity to awareness. Meanwhile, in our era, this ancient courier has finally wandered close enough that a technological species born of another comet-rich world can study it in detail. We are unpacking its spectral package with telescopes, reading the label on material that may once have splashed onto other oceans. And right now, as it hides behind the sun inside a storm of solar plasma, that cargo of water and carbon is being heated and rearranged once again. Whatever happens next will add a fresh chapter to a story that began when the galaxy was young. Up to this point, 3I-Atlas has sounded like an astronomer's dream and a theorist's headache. For the people who worry about rocks hitting Earth, it became something else as well. A live fire drill with a target that should not matter. Planetary defense systems were built to spot and track bodies that could hurt us. Yet here they are, fully engaged, following an object on a one-way escape path that never comes near our planet. On paper, it is harmless. In practice, it has triggered the most intense comet monitoring effort in history. Planetary defense is not a sci-fi phrase. It is the real name of the network of telescopes, computers, and agencies whose job is to notice dangerous objects before they meet our atmosphere at 30 kilometers per second. They look for near-Earth asteroids, measure their orbits, and update impact probabilities. When an object is confirmed to pose no threat, it usually drops out of their priority list. Attention moves on to the next rock. 3I Atlas refused to leave the stage. The key moment was the notice sent out on the 23rd of October. In dry, official language, NASA and the International Asteroid Warning Network announced that a planetary defense observation campaign was being activated for 3I Atlas. The justification sounded modest. The object presents unique challenges. Its behavior is unusual. This is a chance to exercise global coordination and refine our methods for tracking fast movers with uncertain forces acting on them. Read once, it feels like a training exercise wrapped around a rare comet. Then you hit the phrase that many people glossed over. Due to unique problems which 3 Atlas creates, global exercises will be conducted. Unique problems. Not unique science, not unique opportunity. Problems. That is an odd word to use about something that, according to all public trajectory plots, does not come anywhere near Earth. For the mission designers and risk analysts in the background, those problems start with prediction. Every orbit you compute depends on knowing all the forces acting on an object. With this comet, the forces are playing tricks. We know how to handle outgassing for most comets. When sunlight heats, their surfaces, jets of gas, erupt in random directions. That produces tiny pushes that nudge the orbit. By watching how brightness changes with time, you can estimate how strong those jets are. Then you add a correction term into the equations that update the path. It is a messy but well-understood process. For 3I Atlas, the non-gravitational push does not line up with those expectations. The thrust is too smooth, too steady. It looks less like a natural sputter and more like a small engine left on for a long time. Tom Statler, the NASA scientist leading much of the work on this object, has been carefully measured in his public comments. He insists that everything we see can be made to fit natural comet behavior if you are willing to stretch the models and accept that interstellar comets may be weirder than local ones. Officially, there is no evidence of anything artificial. Unofficially, according to astronomers who have worked with the data, there is plenty of debate about what exactly is doing the pushing. When your job is to anticipate threats, a body that refuses to match the template becomes a test case, whether you like it or not. Add to that the shape of the trajectory. By now, you know the pattern by heart. Close pass by Mars in early October. A planned encounter with Venus in the first half of 2026. A later swing by Jupiter. Each pass is close enough for scientific instruments to get a good look, but not so close that gravity yanks the object wildly off course. If you were designing an automated scout to tour the big planets and then leave, you might sketch something that looks very much like this. Statistically, you can still call it coincidence. For sensible people, it is a hint that this particular comet is a perfect stress test for planetary defense logic. Then there is the hiding act. 3I Atlas slips behind the sun at almost the exact moment a huge solar storm is launched in its direction. It will remain out of direct view for weeks, during and after the plasma impact. There are no spacecraft in the right place to give us a continuous live feed. For the men and women who are paid to know what is happening in our cosmic neighborhood, this is a deeply uncomfortable feeling. The most interesting object they have ever tracked is undergoing a dramatic event in a blind spot. That is why the planetary defense framework matters here. It is not just about deflection hardware and impact forecasts. It is about building habits of global coordination and rapid response. When NASA asks observatories all over the world to prepare for intensive monitoring, the moment 3I Atlas reappears, they are not doing it only for curiosity. They are rehearsing how you would react if the next interstellar visitor came in on a path that did cross Earth's orbit in a dangerous way. The comet is both a mystery to solve and a scenario to practice. One more quiet detail reveals how seriously everyone is taking the strange side of that mystery on the public priority lists. You see familiar items, measure the composition, track the outgassing, check for structural changes, refine the orbit. Behind those headlines, according to multiple astronomers, sits an extra line that is rarely spoken aloud in press releases. Listen for anything that might sound like a deliberate signal. That means giving radio telescopes time not just to measure thermal noise, but to search for narrowband emissions and repeating patterns, the classic signatures that the search for extraterrestrial intelligence has hunted for around distant stars. No one expects to hear a beacon. The chances are tiny. The object is ancient. If it ever carried working hardware, it might have died billions of years ago. Even so, the planetary defense exercise quietly includes the possibility that this is not just an inert rock. When the most hard-headed risk managers on the planet decide that checking for techno-signatures is worth adding to their to-do list, the situation has moved beyond a normal comet flyby. So planetary defense cares about 3I Atlas because it behaves like nothing else in their catalogue. It arrived from outside the sun's grip. It refused to coast quietly. It chose a path that looks uncomfortably deliberate. It vanished into a solar storm just as our instruments lost sight of it. And it has become the focus of the most coordinated observation campaign ever planned for an object that will never strike us. The point is not panic. The point is that when the universe hands you a test object this strange, you use it to find every weakness in your system. While 3I Atlas hides behind the sun, the people who study it are doing something very human. They are making plans. When it comes back into view in mid-November, there will be no casual glances, no one telescope quietly taking a few snapshots. What is waiting is a full-scale stakeout of the sky, a coordinated ambush of photons and radio waves. Every major instrument that can spare time has been booked, like cameras set along a dark road where something important is about to drive past. The moment the comet clears the sun's glare enough to be seen from Earth, a global campaign snaps into action. Observatories on 6 continents have been given windows and instructions. In space, the James Webb Space Telescope has carved out precious observing slots. Hubble has time set aside. On the ground, giant mirrors in Chile, Hawaii, the Canary Islands, and elsewhere will all turn to the same moving point. For a few nights, this one object will outshine galaxies and quasars on the priority list. First priority is simple but critical. Where exactly is it, and how fast is it moving? By combining optical measurements from many sites, plus radar pings from facilities like Goldstone and Green Bank, astronomers can pin down its position with astonishing precision. That lets them compare reality to the path predicted before the solar storm. If 3I Atlas is exactly where gravity and known outgassing say it should be, the case for a normal comet gets stronger. If it has wandered even a little too far from that path, the mystery deepens. Almost in parallel, the spectrographs go to work. These are the instruments that stretch light from the coma into bands and lines that act like a barcode for chemistry. They will check the familiar mix of water, carbon dioxide, carbon monoxide, and other gases that were seen before conjunction. Did the giant plasma wave from the sun change those ratios? Did it burn off some materials and expose others? Did new molecules appear that had not been active before, hinting at layers we have not yet sampled? There is a stranger possibility on that list. Scientists will be watching for emission lines that do not match any known atom or molecule, or that appear in patterns that look suspiciously deliberate. If you wanted a comet to whisper that it was built and not born, one subtle way would be to lace its outgassing with unusual species that glow at precise, unnatural wavelengths. No one expects this. The odds are tiny. Yet the observation plans include checks for exactly this sort of spectral weirdness, because with an object this strange, it would almost be irresponsible not to look. Then come the radio ears. Arrays like the Very Large Array in New Mexico, Meerkat in South Africa, ALMA in Chile, and China's enormous fast dish will all listen in the relevant directions. Officially, they are measuring thermal radio emission, the natural glow of warm dust and gas. Quietly, they will also search for narrowband signals and repeating structures. the classic hallmarks of artificial transmission. It is the same technique used to scan distant stars, now turned inward to examine a single fast-moving target in our own backyard. All of this effort is built around a simple question with 4 broad answers. What story will the returning comet tell? In the most uneventful future, 3I Atlas reappears looking exactly like a battered but natural comet should. Its brightness has changed in ways that match the energy dumped into it by the plasma storm. Its tail may be broader or more chaotic. Its spectrum may show slightly rearranged chemistry. But every piece of data slots neatly into known physics. Papers get written. Models of interstellar comets improve. Humanity shrugs and moves on. In the second future, things get odd but remain comfortably explainable. Maybe the plasma impact triggered chemical pathways no one had modeled, producing exotic molecules that still fit within natural chemistry once you understand the conditions. Maybe the trajectory shows mild anomalies that turn out to be the combined effect of strange composition and uneven erosion. The tension in this path comes from details that stretch our theories without breaking them. The comet stays firmly in the natural category, but it forces us to admit that nature has a bigger imagination than we thought. The third future is the one scientists quietly dread and secretly crave. In this branch, the data refuses to sit down nicely. The trajectory might show a pattern of small velocity changes that cannot be made to match any reasonable outgassing model. Or the spectrum might reveal emission features that do not correspond to known substances, yet also do not lead cleanly to an artificial explanation. Radio observations might pick up signals with structure, but not enough structure to convince a cautious community that they are intentional. We would be left with a stubborn maybe, a puzzle that neither side of the natural versus artificial argument can claim cleanly. The fourth future is the world-changing one. Here, something emerges from the data that is so sharp, so far beyond natural processes, that the scientific consensus has to move. A shift in trajectory that maps exactly onto what you would expect from a controlled burn at perihelion. A radio pattern that encodes mathematical sequences no random plasma cloud could produce. Spectral lines from materials that require manufacturing, not condensation in a disk. In this future, the question would not be whether 3I Atlas is artificial, but what that means for us, and what, if anything, we can do about it before it vanishes back into the dark. The odds heavily favor the first 2 futures. The universe is usually more patient and less dramatic than our imaginations. Yet the entire global stakeout is built on the understanding that even a tiny chance of the third or fourth outcome is worth serious preparation. That is why so many telescopes are booked. That is why planetary defense planners folded techno-signature checks into their exercise. That is why astronomers who normally spend their nights studying distant galaxies are happy to point their instruments at a single moving point of light instead. The most interesting part may be this. Even if the data falls into the calmest, most natural bucket, the way we reacted will leave a mark. A worldwide rehearsal for responding to a truly anomalous object will have taken place. Networks will have been tested, protocols refined. Young scientists will have been trained in how to keep an open mind without leaping to conclusions. And if the outcome lands somewhere between reassuring and unsettling, with hints that refuse to vanish, then this stakeout will become the starting point for a much longer conversation about how we handle cosmic uncertainty. Up to now, it has been possible to keep the question safely theoretical. Maybe 3I Atlas is artificial, maybe it is not, we will see what the data says. But imagine yourself on the night the results come back and they are unambiguous. The trajectory changes require controlled thrust. The radio spectrum carries a clear mathematical pattern. The chemistry shows manufactured materials. At that moment, the story of this comet stops being only about astronomy. It becomes about us. How ready are we, really, for a universe that answers back? For most of human history, the idea of other minds among the stars has lived in myths, religions, and science fiction. It shaped stories, not policies. Governments did not have a department for dealing with ancient probes. Schools did not teach guidelines for responding to messages from 1 billion years ago. Even now, when you hear the phrase extraterrestrial intelligence, it probably conjures movie scenes more than it does real budgets or treaties. Confirmation that 3I Atlas is artificial would drag that idea out of the realm of speculation and drop it into the middle of everyday life. The first impact would be psychological. We are used to being the only known technology makers. Our telescopes show us dead craters, gas balls, and barren rocks. Even the most promising exoplanets are just dips in starlight and faint spectral hints. If this comet turns out to be a relic of engineering, then the universe suddenly feels more crowded. Not in the sense that ships are about to arrive, but in the deeper sense that someone else has already played this game and sent their work out into the dark. You and I would have to adjust our mental map of reality to include the fact that we are not the first. Different communities would absorb that shock in different ways. Some religious groups might see it as confirmation of a creator who seeds life widely. Others might feel threatened, as if the uniqueness of human beings had been downgraded. Philosophers would dust off old debates about what it means to be a person, when the category of person expands beyond one species. Politicians would scramble to control the narrative, because the first story told about an event often sticks hardest. Is this a discovery of neighbors, of gods, of ghosts, of potential enemies, of long-dead ancestors? The answer you choose shapes what you do next. Then comes the security question. A probe that has been drifting for billions of years is almost certainly not sending active scouts or aiming weapons. By the time we find it, whatever built it may be gone, transformed, or uninterested. Still, the words planetary defense would take on a new flavor. You cannot look at an engineered object from another star and avoid wondering whether more recent artifacts are also moving through space, perhaps more capable and closer than we think. The conversation about surveillance would stretch from near-Earth asteroids to the entire sky. There is also the darker, quieter fear. If this probe is old and its makers are silent, what happened to them? Did they burn out? Did they ascend into some incomprehensible state? Did they run into something hostile? The galaxy might start to feel like a forest at night, full of unseen watchers. A discovery meant to answer the question, "Are we alone?" could open a different question that is much less comforting. If other civilizations send probes, why do we not see more of them? And why are they so quiet? At the same time, the discovery would be an extraordinary unifying opportunity. For once, every country on Earth would be looking at the same data. No one owns the sky. Every telescope that tracked 3I Atlas would have a piece of the story. It is hard to imagine any other event that could so quickly create a shared human focus. Climate change is slow. Pandemics, as we learned, divide as much as they unite. An ancient artifact from another star system is different. It does not care about borders. It does not vote. It does not choose sides. It invites us to see ourselves as one species trying to understand a message from deep time. There would also be practical temptations. Even if we cannot catch the object with current rockets, engineers would immediately start sketching ways to do better next time. Faster propulsion concepts would get a surge of attention. Nuclear thermal engines, solar sails, fusion drives, even more speculative ideas would move from paper toward hardware with new urgency. The thought of letting another artificial visitor just drift by without a close inspection would suddenly feel irresponsible. 3I Atlas could become the motivator that interstellar travel advocates have been waiting for. The strangest part might be how ordinary life continues around the edges. People would still go to work, argue online, worry about rent, plan vacations. The stock market would still twitch up and down. Children would still learn to read. Yet in the background, a new sentence would have been added to the story humans tell about themselves. Once, a long time ago, something made by another world passed through our sky. We saw it, we measured it. For a brief moment, two branches of the galaxy's history touched. Are we ready for that? Technically, more than you might think. Our instruments, our data analysis, our ability to coordinate globally have never been better. Emotionally and culturally, the answer is less clear. Some of us will reach for wonder, some will reach for fear, most will move, jittering between both. What matters most in that moment is whether we can keep our curiosity open without letting panic or wishful thinking close the case too early. Because even if the answer is artificial, 3I Atlas is not a threat to be fought or a savior to be worshipped. It is a question. A very old, very complicated question written in ice, rock, carbon, and motion. Our readiness is measured not by how loudly we react, but by how well we can listen. Imagine the most ordinary outcome. The data comes in, the global campaign unfolds, every telescope does its work. In the end, the verdict is calm. Atlas is a comet. A wild, extreme, chemically exotic comet from another star, but still a natural object doing natural things in a universe that has had billions of years to get creative. No prime numbers beamed across space. No artificial alloys hiding in the spectrum. No impossible course corrections, just ice, rock, gas, and gravity. On the surface, that sounds almost disappointing. After all this waiting, all this speculation, we get a weird snowball and nothing more. But look closer at what that would really mean. A natural explanation does not erase the strangeness. It confirms it. It tells us that the galaxy routinely produces objects older than our sun that can still roar to life under a new star. It shows us that protoplanetary disks can bake away water and still pack carbon dioxide into comets 8 times richer in that gas than anything nearby. It proves that material can wander between stars for 7 to 10 billion years and still carry chemistry that matters. This is not a letdown. It is a revelation about what nature does when no one is watching. The act of chasing this comet has already changed our tools. Survey telescopes are being pushed to detect smaller and fainter interstellar visitors. Observation schedules that once focused almost entirely on local asteroids now carve out time for these one-time guests from the deep between, stars. Software that used to assume that all comets behave like solar system residents is being rewritten to handle much stranger inputs. Even if 3I Atlas turns out to be the most natural object imaginable, it has forced us to upgrade our curiosity. It has also sharpened our sense of how much we do not know. Before Oumuamua, interstellar objects were an idea in textbooks. Before Borisov, we had never seen a truly interstellar comet up close. Now, within less than a decade, we have 3 very different examples. One dry and rocky and oddly shaped, one icy and familiar, one huge, ancient, chemically inverted, and dynamically odd. From those 3 samples alone, we can already tell that the galaxy's inventory of wandering bodies is far more diverse than we assumed. That diversity reshapes how we think about planetary systems. Our solar system is no longer the template. It is just one arrangement among many. Somewhere out there are stars whose comets carry almost no water, others whose debris is loaded with exotic ices. Some may have belts of objects that rarely wake up at all. Others might constantly fling out pieces that drift between stars for billions of years. 3I Atlas is a data point in a vast pattern we are only beginning to see. On a more human level, this comet has acted like a lens for our imaginations. It has shown us how quickly we leap to stories, how eager we are to project intention onto motion and purpose onto coincidence. It has revealed that serious scientists can entertain radical possibilities without abandoning rigor, and that good skepticism is not the same as closed-mindedness. Watching the discussion around this object is like watching the scientific method in real time. Messy, argumentative, uncertain, and yet slowly converging on better understanding. The planetary defense exercise wrapped around 3I Atlas will not vanish when the comet does. The habits built during this campaign will remain. Agencies now have experience coordinating a rapid, multi-wavelength response to a fast-moving, poorly understood object. They have tested communication channels between civilian observatories, national space agencies, and even military radar installations. The next time something strange appears on the edge of our system, whether it is a natural rock with our address in its future path or another interstellar visitor, we will be faster and smarter because of this rehearsal. Even if everything about this comet ends up falling inside the boundaries of known physics, it still stretches those boundaries. It pushes us to refine our models of how volatiles survive in interstellar space, how radiation reshapes ice over deep time, how complex chemistry can be preserved and then awakened under new sunlight. It makes us reconsider how often material moves between stars and what that might imply for the spread of life's ingredients. In that sense, 3I Atlas is doing exactly what the best scientific puzzles do. It is forcing our theories to grow. There is also a quieter gift. For a brief period, millions of people who rarely think about orbital mechanics or molecular spectra found themselves wondering about an object older than Earth being hit by a wave of plasma behind the Sunday. They asked whether it could be a probe. They learned words like hyperbolic trajectory and Oberth maneuver. They looked up at the sky and felt, maybe for the first time in a while, that something genuinely unknown was unfolding out there. That feeling matters. It is the raw fuel for every future scientist, engineer, and curious mind who will pick up where this story leaves off. So if 3I Atlas is just a comet, it is not just a comet in any trivial sense. It is a bridge between star systems. It is a sample of geology from a world that no longer exists. It is a test of our instruments, our coordination, and our patience. It is a mirror that shows us how small we are in time and space, and how large our questions can still be. Whether or not it carries any message from an ancient civilization, it absolutely carries a message from the universe itself. The message is simple. You have only just begun to understand me. Keep going. When this visitor finally recedes into the dark, its orbit around the galaxy will continue, indifferent to whether anyone is watching. Our story with it will close. Papers will be filed. Data will be archived. New missions will be proposed. Somewhere, another faint point of light will enter a survey image, and the cycle will begin again. That is how science works. Not with a single moment of revelation, but with a long chain of questions, each one pulling us a little further into the unknown. 3I Atlas may or may not change everything in one dramatic stroke. What it definitely changes is us. It reminds us that we live not on a static stage, but in a dynamic, evolving cosmos, full of travelers and stories that began long before we arrived. It invites us to pay closer attention, to build better tools, to ask sharper questions, and to stay curious even when the answer is simply that nature is stranger and more inventive than we imagined. And in the end, that realization might be just as profound as any alien signal.